before we start going off into things outside of our solar system, I want to take a few steps back because I found this neat picture of the sun over here. And the reason why, at least in my mind, it's kind of mind-blowing is because at this scale, the sun is obviously still a huge object at this scale. The Earth would be roughly, and this is an approximation, roughly that big. And so for me at least, this is mind-blowing because it's this idea that our whole planet, everything could fit into one of these kind of plasma flares coming off of the sun. And you can only imagine, I mean, we can't realistically be there, but if you were in some type of protected capsule, what it would be like to be in this type of an environment. So I just thought this was kind of a fascinating concept. But anyway, with that out of the way, let's just think about what it means to be at the boundary of the solar system. In the last video, we explored the Oort belt, which was about, it started a little under 1 light year away from the sun. But depending on what you view as the boundary of the solar system, it could be something way farther in, or it could be something as far out as something like the Oort cloud. So if the sun, right, we see these things being ejected, but even in unseen ways, or unseen particles, super high energy electrons and protons are also being ejected from the sun at super high velocities, 400 kilometers per second. Let me write that down. 400 kilometers per second. And on Earth, we're protected from these highly energetic particles because of Earth's magnetic field. But if you're on the surface of the moon when the sun is on top, and you're not on the dark side of the moon, and you'll have direct contact with these. And as you can imagine, it's not the best thing to hang around in too long. But the whole reason why I'm even talking about these charged particles that are coming out at huge velocities from the surface of the sun, these are considered the solar wind. These are the solar wind. And I'll put wind in quotes, because it's really very different than our traditional association of a nice breeze. These are just charged particles that are going out at super high velocities from the sun. And I'm even going into the idea of the solar wind because to some degree they can help us. They can help us with one definition of maybe the limits of the solar system, and that's the limits of how far the solar wind is getting before it kind of comes in confrontation with the interstellar medium. And this right here shows a depiction of that. So the Oort cloud, it was way, at least the edges of the dense part of it is way outside of this. This is, as we saw, this is just where Voyager 1, Voyager 2. If we wanted the orbit of Sedna, it would be something like, the close part would be something over here, and then it would go out. But the Oort cloud is much, much further out. So if you look at this kind of view of the solar system as the extent of the solar wind, it's much smaller than the Oort cloud, but it's still fairly large. So this is right here, this Heliopause right here, and I got this from Wikipedia. This is essentially where the velocity and the forces of the solar wind are counteracted, that the pressure is so diluted at this point that it's counteracted by mainly the hydrogen and the helium that's in the interstellar kind of medium that's just kind of out there. So this is, after this point, it's not really being injected out anymore. It's kind of being, there's this kind of pause, I guess you could say. And Voyager 1 and Voyager 2 have essentially gotten pretty close to, people believe, that pause over there. And so that's one view of the edges of the solar system. There's never going to be any hard edge to it. Another view would be something like the Oort cloud, the area where you have the still objects out there. And this is all, actually, we haven't directly observed objects in the Oort cloud. We think that they're out there. And then maybe the most abstract definition would be a significant influence from the sun's gravitational pull. So all of those ways are to imagine the extent of the solar system, but they all kind of leave a gray area for what is and what is not in the solar system. But my whole point here, what I want to do is start exploring a little bit outside of the solar system and just give you a sense of the scale as we just go to the closest star. So if we go right over here, this shows our local neighborhood from a stellar point of view. And even though these stars look pretty big, if you actually were to draw this is our solar system right here. But clearly, and you might be saying, oh, maybe that's the sun. No, the sun, if you were to draw it here, it wouldn't even make up 1 pixel. In fact, the entire orbit of Pluto, everything inside of it still would not make up 1 pixel on the screen right here. What we see right here, which is a radius, it's roughly a radius of about, give or take, a light year. This is roughly maybe the radius of the Oort cloud. And we saw in the last video how huge that was, especially relative to the radius of, say, Pluto's orbit, which is roughly like that. And that itself is a huge diameter, or huge distance away from the sun. And that wouldn't even make a pixel. On this diagram right over here. But just to give you an idea, of how far we are. So, we're a speck of a speck inside here, of a pixel in the center of here. To make it from our solar system, or in particular from Earth maybe, to the nearest star, or maybe the nearest cluster of stars, the Alpha Centauri. They're the nearest cluster of stars. There's 3 stars: Alpha Centauri A, which is the largest, Alpha Centauri B, and then there's one that you can't observe with the naked eye, Alpha Proximus, or I think it's Proximus Centauri, I think is what it's called. Not Alpha Proximus, Proximus Centauri. But that's a much smaller star. But that's the closest star, and it's about, and this whole, well, you could view it as this whole cluster of stars right here, and they're the closest, is about 4.2 light years away. Or another way to think about it, if someone were to shine a light on one of these planets, and assuming that light could get to us, it would take 4.2 years to get to us. Or if these guys just disappeared or blew up, we wouldn't know it for 4.2 years. And you might say, hey, that's not too bad. We should take a trip over there and check them out, see if there are any other people there that we can meet and exchange technologies with, or whatnot. But this is a huge distance. Just this 4.2 light years is an unbelievably ridiculous distance. And just to give you a sense, the Voyager 1 and 2 we talked about in the last video, and we can even see how far they've gotten. They've gotten pretty much to the Heliopause. These guys are traveling at 60,000 kilometers an hour. 60,000 kilometers an hour, which is the same thing as 17 kilometers per second. 17 kilometers per second. If we were able to get up to those type of velocities, and these guys got up to those type of velocities by leveraging the gravitational pull of some of the larger planets to accelerate and keep accelerating. So this is a pretty hard velocity to actually reach. But if you were able to reach that velocity and go straight in the direction of the Alpha Centauri system, the closest stars to Earth, it would take you 80,000 years traveling at the same velocity as Voyager 1, which is the fastest of the Voyagers. So it's a ridiculously long time. So it's going to be, we're going to have to figure out some better way to do that.